Alrighty, welcome back, physicists. Today we're going to do an introduction to the magnetic field and just talk about the history of knowing about magnetism. Magnetic fields are another integral part of circuits. They help us do daily tasks. Magnetism is also my favorite part of E&M, and I especially love electrodynamics, which is really just a combination of electricity and magnetism. As a kid, I always loved playing with magnets, and I think a lot of people can relate to that because it's fun to watch them push each other away when you have the like poles together. So let's go over some magnetism basics. We'll look at how compasses work, and then in class I'll have you use circuits to deflect a compass needle, and then we'll just define the magnetic field. So one thing to note is that magnetism is not the same thing as electricity. Magnetic poles and electric charges do share some similar behavior, but they're not the same. Magnetism is a long-range force, and remember, long-range forces we call field forces. And magnets have two poles. We call them north and south. Opposite poles will attract and like poles will repel, just the way opposite charges attract and like charges repel. One thing to note, though, is that in nature, there's no such thing as an isolated magnetic pole. So electric charge exists as what we call a monopole. So like a proton by itself would be an electric monopole. And then if we put a proton and an electron together, that would give us a dipole. Magnetism only exists as like a dipole or a quadrupole. You cannot have like an isolated north magnet or an isolated south magnet. They're always going to come together. So there's no such thing as a magnetic monopole. And we will learn how to mathematically say that there are no magnetic monopoles. If you just have a random bar magnet laying around, you can identify its poles using a compass. We call materials attracted to magnets magnetic materials. And then the most common magnetic material is iron. So iron again is Fe, and we call that ferromagnetism. Magnetic materials are attracted to both poles of a magnet. This is how like you can stick a refrigerator magnet on. Let's talk about how a compass works, because a compass itself is actually just a tiny little magnet that's allowed to rotate. So the north pole of a compass needle is actually attracted to the geographic north pole of Earth. If the north pole of the magnet is attracted to the north geographic pole, what that means is that geographic north is magnetic south. So we actually have to start like magnetic direction and geographic direction are kind of opposite. So geophysicists actually think that Earth's magnetic field is due to moving charges in Earth's core. So if you remember from an earth science class, or if you've never studied earth science before, at the very center of Earth is a solid core, but around that, the outer core is like a liquid nickel and iron hybrid. And so we think that the charges moving in there are what is producing Earth's magnetic field. Earth's magnetic field has reverse pole many, many times in Earth's history. So the way our magnetic poles are now aren't necessarily how they've been in the past. And we can tell that due to the way iron is aligned in rocks, and it also wanders. So magnetic north, or like where the magnetic poles are, wanders all the time. All right, in the 18th century, some scientists were starting to speculate that magnetism was related to electricity. So remember, the 18th century, those are the 1700s. That's when Faraday was active. And the discovery of magnetism, like the first time people really understood that there was some relationship between magnetic fields and electricity, was during a class lecture by a guy named Hans Christian Ørsted. He was demonstrating batteries in a lecture. Batteries were a brand new invention at the time. He happened to have a compass near the wire, and then he noticed that as he closed the switch on his circuit and had current moving through it, the compass near the current carrying wire had it deflected the compass. So that was where we started to really think that magnetism and electricity were related. All right, let's start actually describing the magnetic field. So one thing to note, all semester, three-dimensional and multivariable calculus has been right there touching the surface of what we're doing. It is even more so in this unit. There are a lot of dot products with electricity. There are a lot of cross products with magnetism. So again, you don't have to have multivariable calculus under your belt to do this class. What that does mean, though, is taking things from three-dimensional calculus to one-dimensional is kind of a pain. And that is the hardest part of this. So we're going to define the magnetic field as B vector, and it has the following properties. A magnetic field is created at all points in space surrounding a current carrying wire. The magnetic field at each point is a vector, and we call the magnitude of that vector magnetic field strength. And that would just be a B without the vector harpoon. Magnetic fields exert forces on magnetic poles. The force on a north pole is going to be parallel to the magnetic field, and the force on a south pole will be anti-parallel to the magnetic field. So remember, anti-parallel is just when two vectors are parallel but point in the opposite direction. Magnetic forces cause a compass needle to become aligned parallel to a magnetic field, with the north pole of the compass showing the direction of the magnetic field at that point. And then we can picture magnetic fields using magnetic field lines. So if I draw a little bar magnet here, and then I label this as the North Pole and this as the South, my magnetic field will come out of the North Pole and go toward the South Pole. And just like with electric field lines, lines closer together mean a stronger field strength. And then the field lines can never cross. So when it comes to currents and magnetic fields, we're going to use one version of the right-hand rule. So to find the direction of a magnetic field due to a current carrying wire, we point our thumb of our right hand in the direction of the current, and then we let our fingers curl around. And the magnetic field will be tangent to that circle that our fingers curl around. So our magnetic field at each point is tangent to that circle, but we just draw it as a closed circle. So if I have current coming out of a page, so a vector out of the page, we're going to label as a circle with a dot in it. And a vector going into the page, we're going to do as a circle with a cross. Because if you think of like an arrow from like a bow and arrow, if an arrow is pointing at you, you literally just see the tip of the arrow like a point. And if it's pointed away from you, you see like the feathers and the little fins. That's what the cross is supposed to be. So if I have a current coming out of a page, I'm going to have my current coming out of the page. So I line up my thumb coming on top of my paper and going up. That would be the current coming out of the page. And then my fingers are going to curl around counterclockwise. So my magnetic field is going to be like this. So I'm drawing this with all those little vectors tangent, but we're just gonna actually just say that the magnetic field is counterclockwise, CCW. If I look at a current going into the page, I take my thumb and I actually point it down into my paper, and then my fingers are going to curl around clockwise. So then my B is going to be like this. And then again, most of the time when you're drawing this, you would just draw a circle around the wire with an arrow pointing in the direction. But I just want to show you that what's actually happening is you have that vector kind of tangent to the circle at each point. So you can kind of tell if I have a current carrying wire producing a magnetic field, what that means is moving electric charge is the source of magnetic fields. The magnetic field of a moving charge is given by the equation. We have B vector equals mu naught over 4 pi. And then we're going to say QV sine theta over R squared. So we get the direction given by the right-hand rule. Right-hand rule. Mu naught is called the permeability of free space. And then this is 4 pi times 10 to the negative 7. So just like epsilon naught was like permittivity of free space, it described how well an electric field can go through a medium. The permeability of free space, mu naught, tells you how well a magnetic field can go through a medium. Q is your charge here, and then V is your speed of the charge. And then R is your distance from the moving charge. So we can actually rewrite this in terms of a cross product. This is called the Biot-Savart law. So BO Savar. And we can rewrite this as mu naught over 4 pi QV cross R over R squared. So let's actually just highlight that. The unit of the magnetic field is the Tesla. And 1 Tesla, we call that just 1 capital T. This is defined as 1 Newton per amp meter. Some typical magnetic field strengths, Earth is about 5 times 10 to the negative 5 Tesla. A fridge magnet is about 5 times 10 to the negative 3rd Tesla. So yes, a magnet on your fridge is a stronger magnetic field than Earth. Lab magnets are anywhere between 0.1 to 1 Tesla. MRI magnetic fields are about 2 to 3 Tesla. And then superconducting magnets are around 10 Tesla. All right, so for our first example, we have a proton moving with velocity v 1 times 10 to the 7 I hat meters per second. As it passes the origin, we're going to find the magnetic field strength at the XY positions 100 millimeters, 010 millimeters, and 110 millimeters. So a proton's charge is 1.6 times 10 to the negative 19 coulombs, and this is in the X direction. So the first thing I'm going to do actually is draw this out, define a coordinate system. I'm going to call up positive y, and then I'm going to put positive x back, and then I'm going to put positive z here. So this dot here is going to be my proton, and then it is moving directly on the x-axis. So I want to find B here at 1 millimeter, 0 millimeter, 0 millimeter. I want to find B here, 0 millimeter, 1 millimeter, 0 millimeter. And then I want to find it here, and this is in the XY plane, 1 millimeter, 1 millimeter, 0 millimeter. So first I'm going to look at 1 millimeter, 0 millimeter, 0 millimeter. So if I look, my R vector is going to be this right here. So my R hat vector is the I hat direction. And then my velocity is also in the I hat direction. So what that means is if I have my magnetic field mu naught over 4 pi QV cross R over R squared, parallel vectors have a cross product equal to 0. So sine of 0 is 0. So B equals 0 at that point. At the point 0, 1, 0, my r hat vector this is just 1 times 10 to the negative 3 is my distance. So my r is 1 times 10 to the negative 3 because it's 1 millimeter. And then my r hat direction, my angle between I hat and y hat is 1. So B equals mu naught over 4 pi, and then that's QV cross R over R squared, and that simplifies down to QV sine theta over R squared times mu naught over 4 pi. Sine of theta here, if theta is 1, theta is 90. Let's fix that. I am not really editing this. I decided to just see what it would be like in one go. This is an angle of pi over 2. That gives us a sine theta equals 1. So when we plug this in, we'll do mu naught over 4 pi times 1.6 times 10 to the negative 19 times our v, 1 times 10 to the 7, and then our r, 1 times 10 to the negative 3 squared. So if I take that and plug it in, I'm going to do 4 pi over 4 pi times 10 to the negative 7, mu naught over 4 pi. And then I'm going to multiply that by 1.6 e negative 19 times 1 e7 over 1 e negative 3 squared. So that gave me something a little bit different than I'm used to. Let's see. I flipped that fraction. Let's try that again. 4 pi e negative 7 divided by 4 pi. That's better. I flipped it. 1.6 e negative 19 times 1 e7 divided by 1 e negative 3 squared. There we go. 1.6 times 10 to the negative 13 Tesla. So we would use our right hand rule to find this direction. So if I took my thumb and pointed it in the x direction, my thumb is going in the direction of the velocity of the proton, and my fingers would curl around. So on the y-axis, my fingers would curl around at that point, and they would point directly in the z direction. So this would point directly in the z direction, or in IJK, the k hat. So k hat direction. And then lastly, if we look at the point 1 millimeter, 1 millimeter, 0 millimeters, our r here is going to be root 2 times 10 to the negative 3rd meters. It's going to be root 2 millimeters. So R is root 2 millimeters, or root 2 times 10 to the negative third meters. That's the length of this distance here. And then this theta between V and R is 45 degrees. So sine theta is going to be root 2 over 2. So B, mu naught over 4 pi, and that's Q V cross R hat over R squared, which simplifies to mu naught over 4 pi times QV sine theta over R squared. When we plug this in, mu naught over 4 pi, and then we multiply the charge, 1.6 times 10 to the negative 19, times 1 times 10 to the 7, times root 2 over 2, and then we divide by root 2 times 10 to the negative third squared. So let's do mu naught over 4 pi. Then we're going to multiply by 1.6 e negative 19, 1 e7, and then root 2 over 2, close. And then we have root 2 e negative 3 squared. And that gives us a magnetic field of 5.66 times 10 to the negative 7 Tesla. And then our direction, again, we get from the right-hand rule. So as the proton passes along the x-axis, even at that point, our direction is going to be in the k-hat direction. All right, no, at that point, it'll still be in the k-hat direction, just weaker. All right, our second example, we have a long straight wire carries current I in the positive x direction. We're going to find the magnetic field a distance r from the wire. So I'm going to draw a coordinate system. We'll call this plus x to the right and plus y up. And then I'm going to draw a wire. So here's my wire. I have my current going to the right. I'm going to take this chunk and call this delta x. And then at any point, a distance y from the wire to that point, my r squared is going to be that x location. So we're going to call that xi squared plus y squared, because we're holding that y distance constant, but we're going to be moving along little x's. We're going to call this theta I, and we're going to call this 180 degrees minus theta I. With all these subscripts, you can kind of smell that I'm going to set up a sum. So sine of 180 degrees minus theta I, this is just going to be sine of theta I. And that is going to be my y coordinate over y squared plus x squared. And then if I look at my magnetic field, I have mu naught over 4 pi, and then qv sine theta over r squared. So remember QV, we can look at that as a delta Q delta X over delta T. If I move the delta T over, so I have delta Q over delta T times delta X, I can rewrite that as I delta X. So what Biot-Savart becomes is mu naught over 4 pi I delta X sine theta over R squared. So if I have my little tiny chunks of X, my little tiny chunks of current carrying wire, each little tiny chunk we're going to call a BI is mu naught over 4 pi. We have I delta X, and that's going to be over R squared. So we're going to call that Y squared plus XI squared. And I'm going to multiply by sine of theta. So I have Y over my square root of Y squared plus XI squared. This will simplify BI into mu naught over 4 pi. And then that's going to give us IY over Y squared plus XI squared to the 3 halves delta X. The problem tells us it's a long straight wire, so we're going to assume that that's infinitely long. So when we sum up the BIs to get the magnetic field, we're going to integrate from negative infinity to infinity that expression for BI. The delta X becomes a dx. Let's pull all of our constants out front. So mu naught over 4 pi times IY, integral from negative infinity to infinity of dx over y squared plus x squared to the 3 halves. We're not going to do this type of integral. You really don't want to do by hand. You would want to look it up in an integral table. So look up in table. We get B for a wire as mu naught IY over 4 pi. And then we get this lovely expression, X over Y squared, X squared plus Y squared to the 1 half. Evaluated from infinity, negative infinity to infinity. This will simplify to mu naught I over 2 pi Y. So mu naught times the current over 2 pi times the distance from the wire. And this is our field due to a wire. So we actually get a 1 over y decrease in magnetic field strength as we move radially away from the wire. All right, we're going to finish off with just force due to a magnetic field. Magnetic fields exert forces on charged particles. So it's important to note that the field is external to the field that would be created by the moving charge itself. So in each of these examples, so the first one, there's a proton that's stationary. it's in a magnetic field and there's no force. So magnetic fields exert no force on stationary particles. In this second picture, we have the charged particle moving in the same direction, so parallel to the magnetic field, and still no force. So this means there's a cross product in play. So we can see here, as we start angling the velocity away from B, we get a larger magnetic force until we reach the maximum size force when that angle is 90 degrees. So we get a cross product. So the magnetic field, or the magnetic force on a charge Q, as it moves through a magnetic field B with velocity V, we're going to get QV cross B, or QVB sine theta. And then you get the direction by the right-hand rule. That theta is the angle between V and B. What this means is that the magnetic force on a charged particle is perpendicular to both the magnetic field and velocity. Some important properties of the magnetic force is that only a moving charge will experience a magnetic force. If V equals 0, then FB equals 0. There is no force on a charge moving parallel or anti-parallel to the field. When there is a force, the force of a negative charge will be in a direction. When there is a force, it is perpendicular to both V and B, and then the force on a negative charge is in the direction opposite V cross B. If the charge is moving perpendicular to B, then FB is just QVB. And here is our right-hand rule. So we stick our thumb in the direction of velocity, we stick our index finger in the direction of the magnetic field, and then your middle finger is the force. The right-hand rule works for a positive moving charge. With a negative charge, you're going to use the right-hand rule, figure out the direction of the force, and then you're going to flip that direction for a moving negative charge. So for number 6 here, for the right-hand rule, if I point my thumb in the direction of V, I can't point my finger in the direction of B. These are parallel, so my force is 0. For the second one with the proton moving up, so I stick my thumb up, and then my index finger I point to the right, and then my middle finger is actually pointing down into the page. If I look at the third one, I point my thumb to the right along V, and then my index finger I point down into the page. And then my middle finger is pointing up in the direction of that red arrow. And then for the last one, that's a negative charge, so I'm going to use my right-hand rule. I point my thumb to the right along V. I point my index finger down into the page, and then my middle finger is pointing up, but it's a negative charge, so I flip the direction of the force. All right. we're gonna do one last example. A long wire carries 10 amps of current from left to right. An electron 1 centimeter above the wire is traveling to the right at a speed of 10 million meters per second. We want to know the magnitude and direction of the magnetic force on the electron. So the first thing we're going to have to do is actually use that magnetic field of a wire equation. We have to figure out what the magnetic field due to the wire is. And then we get to find the force. So here's my wire. I got 10 amps to the right. Using my right hand rule, my fingers would curl. So my magnetic field is coming out of the page above the wire, and it's going into the page below the wire. And then I have a little electron here moving to the right at 10 times 10 to the 6 meters per second. So my magnetic field is going to be mu naught I over 2 pi r, where r is 1 times 10 to the negative 2 meters. It's the 1 centimeter above. And then my F is QVB sine theta. But here, I have a 90-degree angle, so it's just QVB. So what I'm going to do is actually combine the equations before I plug anything in. The bell is about to ring. So F equals QVB, QV mu naught I over 2 pi r. And then when we plug in, we get 1.6 times 10 to the negative 19, 10 times 10 to the 6th, 4 pi times 10 to the negative 7 times 10, and then we divide by 2 pi times 0.01. That's 1 times 10 to the negative 2. Let's make a nice little fraction there. .2 times 10 to the negative 16 newtons. And then we're going to use our right hand rule. So where that electron is, my velocity is going to the right, so I point my thumb that way. My magnetic field is coming out of the page, so I point my finger out of the page. And then my force is pointing down. But it's an electron, so I have to flip my middle finger to point up. This is going up. So that's your basics of magnetic field. You're going to do some research on what cyclotrons are, and then we'll do some practice problems.